Morning, everyone. Okay. We'll wait for 2 minutes. Let people join. Just a minute, we'll wait for people to join and then we'll start for a minute or so. Okay. Yes, till then you can ask your doubts from yesterday. You can post your questions. Let's search answers for those. If you've read any, let us see if it's there in the presentation, or else I'll try to clarify those doubts. What's the difference between dispersion toughening and transpiration toughening? Okay, I've kept that slide. I'll explain you in detail about that. Okay. Any more questions from the Pulse or anything what you are reading? Some ambiguous questions, doubtful questions. Those also you can post. One second. Okay. So I've got enough now. So let's start. 30 people now. Okay, so now I'll just briefly, first I'll brief out all these ascending order, descending order type of questions and common ADS specification numbers, which you all to know. Okay. Is cold working, heat hardening, those also we'll discuss. Metal oxides added in porcelain to don't do they increase strength? Yes, metal oxides do increase strength of ceramics normally, but metal oxides are for this opaqueness they provide, like your titanium oxide or boric oxide. Others are added for your opaqueness, but they also increase strength ultimately. Okay, I'm again discussing few questions now here. One second. Now these are the ADS specification numbers of different materials. Okay, I'll send across the PPT to Ashfaq. He'll forward it to you. Okay, Dr. Ashfaq will forward it to you. But just let us discuss what are the different ADS specification numbers. Now one is for amalgam, 2 is for your dental casting investment materials, 3 is for your impression compound, 4 is for your inlay wax, 5 is for gold casting alloy, 6 is for mercury, 7 is for wrought alloys, 8 is for zinc phosphate cement, 9 is for silicate cement, 11 is for agar, 12 is for denture-based resins, 14 is for your cobalt chromium alloy, 15 is for your synthetic polymer teeth, what we're using, 16 is for your ZO impression base, yesterday as I told you, 17 is for your denture relining material, okay, 18 is alginate, yesterday we discussed, 19 is elastomers, you all know, 21 is zinc silico phosphate cement, okay. So these are the first set of ADS specification numbers. Now the next set you have 23 is for dental excavating burrs, 24 base plate wax, okay, 25 gypsum products, okay, 25 gypsum products, restorative resin composites is 26, 28 root canal files and reamers, 30 is ZOE cement, 32 is orthodontic wires, 37 is dental abrasive powders, 38 is your metal ceramic restorative systems, 39 is your pit and fissure sealants, 42 is your phosphate bonded investments, okay, 46 your dental chair, 57 is your endodontic sealants, 78 is your endodontic obturating cones, 100 is your orthodontic brackets and tubes, 110 is your lasers, 113 is your periodontal curers, 119 is manual toothbrush. Okay, these are few ADS special numbers which I could find out and give you up. Okay, sometimes they ask you question from ADS specification numbers, so at least you should know them. These are the few common ones they ask routinely, so it's better if you know them. Okay, now byproducts, if you see, okay, you have polysulfide as water, zinc oxide impression paste is water, byproduct. Condensation silicone is ethyl alcohol, addition silicone is hydrogen, and even amalgam has hydrogen as byproduct. Now in yesterday, as I told you, in addition silicone, what we are doing is you're adding palladium, okay, which acts as hydrogen absorber. As such, for a reaction, there is a byproduct, but because we are adding palladium, so there is no generation of byproduct as such because it is getting binded with your palladium. Okay, the question can be twisted here for a stance. Okay, so remember, see the options clearly when such a question comes. Your amalgam also releases hydrogen. You know all about delayed expansion. Okay, zinc combines with hydrogen and water. Okay, zinc combines with water to form zinc oxide that keeps delayed expansion for your amalgam. Okay, now order of cell toxicity. Now, when we're talking about cell toxicity, polysulfide has the least less than alginate. In alginate also, normal setting alginate has less than fast setting alginate. Okay. Okay. Now, in order of cell toxicity, you have polysulfide, which has less cell toxicity than alginate, which has less than addition silicon, and addition silicon less than your ZOE impression paste, and which is less than polyether. Now, polyether has highest amount of cell toxicity. Okay. Now, this is the descending order of cell toxicity. Okay. Now, linear contraction, again, condensation silicone has highest amount of linear contraction. Then it's polysulfide, then it is polyether, and the least linear contraction is seen in addition silicone. Okay, so this is what you have to remember. Now, dimension stability is a reverse of the linear contraction. Least amount of dimension stability is for your condensation silicone, then it's for polysulfide, then it's for polyether, then it's for addition silicone. Okay. Now, distortion, when you're removing, highest amount of distortion is seen in polysulfide, then it is seen in condensation silicone, then it is seen in polyether, then it is seen in addition silicone. So these are again few questions. I'm just repeating yesterday's thing. Okay. Now, setting times, I've written your setting times here. You can just go through the setting times here. Now, polyether has 6 minutes. Addition silicone has 4 to 6.5 minutes. Condensation silicone has 6 to 8 minutes. Polysulfide has 7 to 10 minutes, which is highest. Okay. In elastomers, fast setting arginate has 1.5 to 2 minutes. Normal setting arginate has 3 to 4.5 minutes. Type 1 ZOE 10 minutes, and type 2 has the highest, that is 15 minutes. If they ask you highest among these materials impression, then if ZOE type 2 is the option, then definitely that goes as highest. Okay, remember, see the options well. Okay, we'll just be in a hurry, polyether only, no, so poly sulfide only, no. Just see all the options, whether ZOE is also there in the option or not. Check clearly. Okay, in the cements, if you come down, then zinc phosphate cement has 2.5 to 8 minutes. Zinc polycarboxylate has 6 to 9 minutes, and your ethoxybenzoic acid, that is non-eugenol based cements, have 7 to 9 minutes of setting time. Now, these are the different compressive strengths. Okay, a tabular column showing the compressive strengths, tensile strength, and elastic moduli of all these different cements. Okay, now cements for your final cementation. See, if they ask you a question, cements for temporary cementation, you have your non-eugenol. Okay, you have your zinc oxide eugenol, and then you also have a resin composite. Resin composite. It is not resin cement. It is a resin composite. Okay. Now, when you're asking cements for final cementation, you have adhesive resin, you have compomers, you have glass ionomers, you have hybrid ionomers, you have resin composites also again, and then you have zinc oxygenol type 2, EB alumina polymer modified. Okay, you have zinc phosphate and zinc polyacrylate. Okay, and zinc polycarboxylate also. Now, if you see here in the compressive strength, okay, the highest amount of compressive strength is to resin composites. Okay, that is your resin cements have the highest amount of compressive strength. Now, if you talk about tensile strength, okay, now tensile is more for your adhesive resins. Okay, again for resin-based cements only. And now elastic modular, if you see, it is more for your hybrid ionomer and adhesive resin, which is variable. Okay, if you take more, then again resin composite only, which has 4.4 minimum. Oh, sorry, zinc oxide eugenol EBA cement has 5.4 and zinc phosphate has highest, which is 9.3. Okay, so these tabular columns you have to go through, where you'll get an idea. Sometimes few questions fall from these tabular columns directly from the textbook. They can ask you the numbers. Okay, I'll send across the PPT, don't worry. Now, solubility in water. Okay, this is one question. What is the solubility in a descending order or ascending order? Okay, these type of questions will come. Which has the least solubility? Which has the highest solubility? Okay. Now, if you see all the here, he have given compomer, they have given glass ionomer, they have given hybrid ionomer, they have given resin composite or the resin cements, they have given zinc oxide eugenol, that is polymer modified, and EBA. Then you have zinc polyacrylate, okay, and zinc phosphate. Now the maximum is seen for zinc phosphate. See, they have given here clearly it is 0.2. Okay, 0.2 is for zinc phosphate. Okay, 0.2 is for zinc phosphate. And if you see, compomer has been given low. Now they have not mentioned if suppose the option is compomer. Okay, if suppose the option is compomer or EBA alumina, okay, or EBA alumina, then if compomer is present, choose compomer. If compomer is not present, then it is EBA alumina, which has 0.04, okay, 0.02 to 0.04. Okay, so clearly see the options again. Okay, clearly see the options again. If they are asking least or highest, highest definitely for zinc phosphate, which has 0.2. Okay, which is 0.2 of solubility, that is 0.2% of solubility in water in 24 hours, that is zinc phosphate. Now if you see setting time at 37 degrees, they have given again setting time here, that is 6 to 8 for his glass ionomer. Okay, 6 to 8 for glass ionomer, compomers is 3. Okay, hybrid ionomer, it is 5.5 to 6 minutes. Resin cement, it is 4 to 5 minutes. Eugenol, again in polymer modified, it is 9. EBA is 7 to 9. Zinc polyacrylate, 7 to 9. And zinc phosphate, 5 to 9. That is 2.5 to 8 again. Okay. So film thickness also, if they ask you which has the least film thickness. Least film thickness. Now maximum is for zinc phosphate. They have mentioned 25 maximum, they are saying. 25 maximum, they are saying. Zinc polycarboxylate has more solubility than zinc phosphate. As per these numbers, it's not mentioned polycarboxylate here. Okay, I'll see for a polycarboxylate and let you know. But in the tabular columns, they have not mentioned polycarboxylate. So I'll just re-verify. I have PPT of cements also. We'll just see through it once again. Okay, till then just we'll brief out what is there in the tables given in the textbook. These are all just textbook values, what I'm discussing now, okay, from Phillips. So we'll just go through these and then we'll just recheck individual cements also, okay. Now if you see the film thickness, now here the least amount of film thickness is for your glass ionomer, okay, sorry, hybrid ionomer, which is 10 to 22, and resin cement also, which is 13 to 22. Both are almost the same. Okay, and maximum here he has mentioned for polyacrylate and your EB alumina as 25 to 35. But here when he has mentioned in the textbook 25 is the maximum for zinc phosphate, means it is definitely always 25 and more. But the other cements can be up to 25 only. Depends on the mix. Now that depends on the mix. Okay, so the film thickness. So remember here he has mentioned clearly for solubility and this the maximum. Okay, so remember those two values. Here he has mentioned the maximum. Okay. Now pH, if you see the pH, okay, which cement has the highest pH or which has the lowest pH over time, if you see the pH after 24 hours, okay, that is the last one after 24 hours, it's the highest for glass ionomer, okay, that is around 5.98, okay, and zinc polycarboxylate, which is 5.94. Now zinc phosphate has the least pH, which is 5.50. But if they ask you But if they ask you immediately after you mix, which has the highest pH, lowest pH means zinc silicophosphate. If you see, it is 1.43. For zinc silicophosphate, it is 1.43, the pH. Okay, the least pH after immediately mixing, 2 minutes after mix, is zinc silicophosphate. So this time variable is given from the textbook only. They have given mention in the textbook clearly. What are the pH values changing? They'll not ask you like 5-10 minutes and all. That is very far off a question. They'll ask you the initial, immediately after mix, and after 24 hours. That's a more common question they can ask you. So remember that that will be one thing they'll be asking you in exams. pH questions are also come previously in AIMS entrance exams and all. So clearly remember, okay, you have to note down the values. If you see immediately after 2 minutes of mix, which has the least pH if they're asking you, would be zinc silicophosphate, and which would have the highest pH. Okay, after 2 minutes of mix, it is zinc polycarboxylate. Okay, so zinc polycarboxylate will have a better pH than compared to other cements. Okay, so remember that that is one another question which they'll ask you. Okay, I'll forward across the PPT. Now, GIC, there are 9 types according to application. This is also one common question. They'll ask you type 1 is what, type 2 is what. Now, type 1 is luting, type 2 is restorative, type 3 is liners, type 4 is fit and fissure sealants, type 5 is orthodontic brackets, type 6 is core buildup, type 7 is stabilizing and root surface protective, type 8 is anterior ART, type 9 is posterior ART or geriatric. Okay, so because posterior ART is high fluoride releasing. Now if they ask you among all these which is the high fluoride releasing, means it is type 9. Type 9 is a high fluoride releasing cement. Okay, it is also used in geriatric and pediatric scenarios. Even in periodontic patients, you will use your posterior ART. Okay, the posterior ART, again, you have to remember that they're asking you. No, it's not type 7. Type 7 is also releasing, fluoride releasing, but your posterior ART is specifically for geriatric and pediatric patients. Okay, fluoride releasing. That is a common mistake we make. Okay. All GICs release fluoride. I'm not saying GICs don't release fluoride, but posterior ART is specifically used for scenarios, okay, where you need for geriatric and pediatric scenarios. Now there's a newer classification where traditional GIC, that's type 1, type 2, type 3, liners and base. Then you have metal modified, in which you have Miracle Mix and Cermet. Okay. Then you have light cured GIC, that is HEMA is added to the liquid. And then you have hybrid or resin modified GIC, in which you have composite resins, in which fillers are substituted with glass ionomer particles. There is one more classification of your GIC. One second. Okay. His GIC is anti-karyogenic because it releases fluoride. Okay, fluorides prevent caries progression. Okay, they are also antibacterial at times, fluoride. So GIC, because of its fluoride release, it is most commonly used. Okay, in high risk cases where you can see there is high amount of caries potential, okay, or decay in the patient. Okay, that's where we use GIC. Okay. Okay, fine. Now, one second. Okay. Now, next you have your relative increasing wear rate. Now, the wear rate, if you see, of the restoration, how rapidly it can wear, then GIC will wear faster. Amalgam has the least wear rate. Amalgam restorations stay for around many years also. Still, it is the best among wear rates. If you take according to the ascending order, that is which has more wear rate, then definitely GIC has more. Then you have resin modified GIC. Then you have Cermet. Cermet because it has slight metal component. Okay, that's a metal modified GIC. Then you have composites. Okay, composite because of their resin structure, more amount of filler contents. They are also having more resistance to wear. And amalgam because of its complete alloy nature, it has more resistance to wear. Okay, so this is what is your relatively increasing wear rates. Okay, if some question comes on increasing wear rates, then you have to know GIC has the highest amount of wear rate. Okay, see the options again. Again, I'm telling you, always see the options very clearly. What is being mentioned there? Okay, always see the option. What is being mentioned. Now, composites, if you see how over the years they have been developed, okay, how they've increased from normal like regular megafill composites to now to the nano filled composites to nano hybrid composites. Okay, so 1950 it started the original development. Then 1960, around 60 to 64, they have macro filled self-cured composites were came into the market. Then around in 1975 they were mid-fill, and then 1978 it was microfill composites. And in 1984 it was mid-fill composites again, which were modified. Then in 1988 or something, they've come out with midi hybrid composites. Then in 1997 they've come out with flowables. In 1999 they were packables. Then 2001 or 2002 they've come out with mini hybrid composites. Okay, and then 2003 they've come with controlled shrinkage prototypes where you had a less amount of shrinkage into the composites. And then around like 2004 or 5 they've come out with nano hybrid composites. So over the years, like down the lane of 60 to 70 years, the composites have developed. They've been developing, improving the composites by the nature of shrinkage, or because composites as such initially when they were discovered, they had a lot of curing shrinkage because it was a resin. Okay, they had a lot of curing shrinkage among composites. You, it would be better if you remember this timeline, I would say, because I mean, I don't know how they are asking it now, because previously when we had AIMS and all exams, they were keen sometimes on asking the timelines. Okay, so this is neat completely now, but if you're appearing for AIMS or other exams also, it will be helpful. Okay, sometimes they see where does the bouncer comes. Everyone will know the basic question. Do you know the advanced question or not? That's the criteria wholly in the exam. Okay, everyone will know the basic question. Everyone will know the basic answer. Everyone has the basic knowledge. You should apply that knowledge correctly. That's the only thing. Very few key questions are there, which we what is there we think, oh, it will not come, but definitely those questions will come in the exam. Okay, every other basic question will be attempted by everyone. Everyone will get correct. That's where the competition happens. Okay, it's a difference of 1 or 2 mark only where we lose the seat. Okay, and then again the agents, okay, the bonding agents also, dentine bonding agents again. You had unbonded composites around in 1964. Then you had acid etching and enamel bonding. Okay, Bunocore. Okay, you all remember Bunocore, yes. Then you had dentin bonding composites in 1980s. Then you have dentin bonding systems. They've been developing over the years. Now we are on the 8th generation of dentin bonding systems. Okay, now we are on the 8th generation of dentin bonding systems. If you take a composite curing also, initially they were self-cured resins only. Then they've started with UV cured. Then we have cured. Then we have started using a visible light cure. Okay, visible light cure composites, that is QTH, PAC, and lasers. Okay, visible light cure composites have been using now. We have been what we are using is now visible light cure composites only. So over generations we've been improving the material as such. Okay, where it has become easier for usage. Okay, so remember these. Okay, if some questions by chance, I'm not saying it will come or not come, but if it comes, you have to know. Okay, the timeline which was come before, like macrofill, midfill, microfill. Okay, that will help. Now, if you take according to the filler particle size, now what is the filler particle size in your composites? Uh, they've asked sometimes, okay, what is the size of megafill? They'll give you the options like 0.5, 10, 9 nearby options. So they can give you that options and you'll get confused among these nearby 0.01, 0.1, 0.1, 0.1, 0.1, 0.2. They'll give nearby options only. So you have to remember these sizes. Now megafill is 0.5 to 2 micrometers. Okay, macrofill is 10 to 100 micrometers. Minifill is 1 to 10 micrometers. Minifill is 0.1 to 1 micrometer. Okay, microns. Microfill is 0.01 to 0.1 microns, and nanofill is 0.005 to 0.01 microns. Now, if they ask you which composite has a variable particle size, then hybrid is the one. Okay, because hybrid is a mixture of other composites like nano and microfill composites, mostly nano or micro and minifill composites. It's a mixture of those. Hybrid is a mixture of those, not midfill and microfill, but mixture of nano and microfill. Okay, so it gives a hybrid its packable consistency and strength. Okay, hybrid has better strength if you take and flow compared to others. Now nanofill, it is more finer particle size. Strength-wise it will less, but flow-wise it is very much better. Okay, flowable composites are mostly nanofill composites only. Okay, now what commercially we've been using, if you have seen in your clinical practice in your UG days in the department, what we are using mostly is hybrid and nanofill composites now currently. Okay, so that is one you have to know about the filler particle size. This is a question which can come, anything can come, like they can ask you megafill size, they can ask you minifill size, they can ask you nanofill size, particle size. So anything can come across as a question. Okay, need not worry about that. Now next, what is the composition of a composite? Okay, now bisphenol glycidyl methacrylate. Okay, BisGMA is the resin matrix in your composite that was given by Bowen. Okay, Bowen was the first scientist who was given with this resin matrix for composites. Okay, in 1960. Now, what was the major disadvantage? Was high viscosity of BisGMA. Okay, and blending of filler particles was difficult. Okay, blending is like packing of the filler particles was difficult. So diluent monomers were added. What was added to this resin matrix was UDMA, that is urethane dimethacrylate, okay, and TGDMA, that is triethylene glycol dimethacrylate. These two were slightly added in amounts to this resin matrix, okay, to give its proper flow, to decrease down the viscosity, and also blending of those filler particles to enhance or improve the blending of the filler particles. So these are the two things. These are, this GMA is the major constituent, okay, in the resin matrix. Anytime if they ask you what is the major constituent, it's this GMA, definitely. And what are the other things which can be added are the urethane dimethacrylate and TGDMA, this stigma, triethylene glycol dimethacrylate. Now fillers, they have different fillers again here. We'll discuss what are they. They're added to improve the strength of fillers. They fill the voids in between the resin matrix. That's why they're called as fillers. Fillers are filling material. Okay, by the name fillers, the meaning fill. Okay, improve the strength, rigidity, hardness, increase in modulus of elasticity, and decrease in coefficient. Okay, decrease in. Sir, can you explain about estrogenicity of BisGMA? Okay, fine. I'll discuss on that. I'll take down to a composite seminar where I'll explain you on estrogenicity of BisGMA. Okay, this seminar particularly, what are the slides I'm discussing and briefing out about dental materials only. I'll discuss in detail about composites and cements after this. Okay, yeah, we'll clear this one also. Now you have decrease in coefficients of thermal expansion and decrease in contraction. These are the these are the things provided by your fillers. Now coupling agents, they bind. Okay, they bind the filler particles to resin matrix. So that's why they're called as coupling. Okay, they bind. They act as a binder. Okay, allow the more flexible polymer matrix to transfer stresses to the stiffer filler particles. Okay, so they help in transferring the stresses from the resin matrix to the filler particles. Okay, they also provide hydrolytic stability by preventing the water from penetrating along the filler resin matrix. They form as a barrier such that any saliva or any water does not go beyond to it. Okay. Relation between modulus of elasticity and filler particles. Okay. That is a table. I'll discuss you with a table, that modulus of elasticity and filler particles. Okay. In the properties, we'll be discussing physical properties of dental materials. Again, I'll discuss modulus of elasticity and then everything again. Okay, then you have methacryloxypropyl trimethoxysilane. Okay, methacryloxypropyl trimethoxysilane as your coupling agent. Okay, remember that. Now, what is the activator initiator system in your composites? Okay, benzyl peroxide is the initiator. Tertiary amine is the activator. Okay. Now, in light activated resins, what is the visible light range? That is 468 nanometers, and the photoinitiator is your camphor quinone. What's the inhibitors in your composites? You have butylated hydroxytoluene. Butylated hydroxytoluene is your inhibitor. Okay, this is just a basic class composition of your composite, basic composition of any composite. Okay, now in gypsum products, yesterday also we discussed about the water powder ratios. Okay, the setting times. Okay, and if you take the compressive strength, okay, it's the highest for your type 5. It's the highest for type 5. Okay, 1 hour post 1 hour compressive strength, it is highest for your type 5. Okay, and setting expansion also, if you see, it is more for your dental stone, high strength, high expansion. Obviously, it's in the name. Okay, and your dental plaster. Okay, that is 0.30 and 0.30 percentage setting expansion. So this is a table directly from your textbook, okay, where it gives simple, very ideally it is explained what is type 1, type 2, type 3, type 4, and what is the water powder ratios. Okay, it is simplified for you to see what it is. Now alloys, alloys again we'll be discussing in detail. I'm just briefing you out what alloys are. Okay, keep up your questions ready if you have any. Okay, in alloys you have high noble, okay, which high noble alloys must contain greater than 40% of gold. Remember, greater than 40% of gold has to be present in your high noble alloys, okay, and greater than 60% weight of noble elements. Now, what are the noble elements? What are the other noble elements? You have gold, you have platinum, palladium, ruthenium, uh, rhodium, iridium, osmium, and silver. Okay, these are all your noble metal elements. Okay, gold, there are 8, total of 8: gold, platinum, palladium, ruthenium, silver. It is considered, it is one of the noble metals. Silver is considered, okay. On gold, platinum, palladium, ruthenium, rhodium, iridium, osmium, and silver. Okay, these are your 8 noble elements, out of which high noble has to contain more than 40% weight of your gold and 60% weight of your noble elements only. Now in noble, it must contain 25% weight of noble metal elements. Now those are your noble metal elements: ruthenium, rhodium, iridium, osmium, okay, and silver also, okay. Predominantly base metal, they contain less than 25% weight of noble metal elements. Okay, so that's why they're called as predominantly base metal alloys. Okay, now this is a classification from the textbook what we've got. Okay, so this you have to remember what is high noble, noble, and predominantly base metal. Then you have mechanical property requirements. This is another classification in which you have type 1, type 2, type 3, and type 4 alloys depending on their yield strength, or proof strength, okay, and percentage elongation. If you see type 1, the yield strength is only 80 megapascals, and minimum elongation after fracture is more, that is around 18% to these alloys. Okay, then you have type 2, where you have yield strength of 180 and minimum elongation of 10. Then you have type 3, which has a yield strength of 270 and percentage elongation of 5. And you have type 4, where the yield strength is 360 megapascals and percentage elongation is 3. Now this also comes for your casting gold alloys. Okay, this is also important. This type 1, type 2, type 3, and type 4 gold alloys, if they ask you based on mechanical properties or yield strength, okay, so then you have to remember the values. They'll ask you how much is the yield strength of type 1 alloys. So then you have to remember it is 80 megapascals. Or if they ask you what's the yield strength of type 3 alloys, then you remember it is 270 megapascals. Or if the percentage elongation is more, for which it is definitely definitely type 1. So this you have to remember. This is also one of the common questions which they'll ask you. Okay, so this is a direct standard textbook reference, so wouldn't be a problem for attempting or correct answering. Now, mechanical properties of orthodontic wires, if you take, now in orthodontic wires, you have stainless steel, you have cobalt, chromium, nickel, you have nickel titanium, and you have beta titanium. And if you're checking about modulus of elasticity, okay, if you're seeing for modulus of elasticity, cobalt, chromium, and nickel alloys have more modulus of elasticity, that is 184 gigapascals. Among everyone, they have 185 and 84 gigapascals. Okay, now nickel titanium has least modulus of elasticity. Okay, now that's why they're more flexible. If you take nickel titanium files, they're very flexible, but because their modulus of elasticity is less, they fracture fast also. Okay, nitai files, you might have all heard about nitai files. Okay, so they have modulus of elasticity least, but their flexibility is more. Okay, now if you take yield strength, that is 0.2% offset, that is GPA. If you take yield strength, it is highest for your stainless steel. If you take yield strength, it is highest for your stainless steel, that is 1.6. Okay, that is 1.6, and for your least for your nickel titanium, that is your 0.43. Now your ultimate tensile strength, if you are seeing for ultimate tensile strength, it is also more for stainless steel, that is 2.1. There is point is missing in all this. Okay, it is 2.1 gigapascals, your ultimate tensile strength. It is more for your stainless steel, and it is least for your beta titanium. So you have to keep reading these tables. Okay, it's not easy to remember because they can ask you a question of modulus of elasticity. I can make a question on yield strength. I can make a question on ultimate tensile strength. Okay, so this doesn't go like this. You have to keep revising this, or else chart it down at one place. Anyhow, I'm giving this PPT. I'll send you this PPT so that you can refer. Okay, this is 2.1 to 1.7, 1.5, and 1.3. They're not 13, 14, 15. Okay, remember that points are missing because of the picture. Okay. There's a slight difference among resiliency and modulus of elasticity. I'll show you the definition, then you'll understand. There's a mild difference among both. Okay, I'll show you the definition, you'll understand the difference. Okay, not a major. If you take property wise or the term unit wise, they're not the difference, but a slight variation. Okay, it is the fracture resistance. Okay, we'll tell you about mechanical properties and physical properties. Again, there are many questions in them which are commonly asked. Okay, now if you're talking about number of 90-degree cold bends without fracture, okay, cobalt chromium can bend more. Okay, cobalt chromium can bend more number of 90-degree cold bends, and it can bend to 8. Okay, so remember these mechanical properties of orthodontic wires. Now, if you're talking about amalgam, now basic composition of amalgam, it contains the basic constituents are silver, tin, copper, and mercury, the alloy. Okay, liquid is obviously mercury. Silver, tin, copper are there in alloy, and liquid is mercury. Now, other ingredients which can be added are zinc, indium, and palladium. Now, what does silver does is it increases strength. Okay, it increases expansion. Okay, and tin decreases expansion, decreases strength. Now, tin is counteracting silver. Okay, tin is counteracting silver, and it is increasing the setting time. Now, tin is helping in increasing in your setting time. Remember that. Now, copper ties up with tin, reducing the gamma 2 formation. Now you have something called as low copper alloys and high copper alloys. Now, if you take comparison to low copper and high copper alloys have better strength because gamma 2 phase is reduced. Because gamma 2 is the weakest phase, they say. Okay, that is also one more question which is commonly asked also, if I remember. Gamma 2 phase is the weakest phase among all the phases of your amalgam. Okay, so copper is added to reduce down that gamma 2 formation, and it also increases the strength. It also reduces tarnish. It improves the resistance to tarnish and corrosion. Okay, it also reduces creep, that is, it reduces marginal deterioration. Now, what is creep? It's a time-dependent plastic deformation of a material. Now mercury, it is activating the reaction. It is a liquid by which it reacts. The silver particles react with the mercury. Only pure metal that is liquid, okay, at room temperature, that is mercury. Now spherical alloys require less mercury. Now in alloy classification also of your amalgam, you have lathe cut, you have spherical alloys, okay, that will tell you now. So depend if you have spherical alloys, because they are even regular shaped, okay, it requires lesser mercury to mix. Okay, small surface area, easier to wet. That's why you require only 40 to 45% of mercury. Now, admixed alloy is a mixture of both. It is lathe cut and spherical alloys. Okay, and lathe cut particles are more difficult to wet, might require more percentage of mercury. Now, zinc, it is used in manufacturing. Okay, it decreases the oxidation of other elements. It is a sacrificial anode. That is, what does zinc do? It decreases the oxidation of other elements. High copper amalgam and brittleness. Okay, what will be the effect of high copper and brittleness? Now, high copper amalgam alloys will improve the strength. Okay, they'll not make the metal more brittle. They'll improve the strength, but in percentage amounts only. Your copper cannot be more than 30%. Okay, if it is more than that, then it causes brittleness. Okay, if it is more than 30%. Normally, it is not placed beyond 30% in any of your amalgam alloys. If it is goes beyond 30%, yes, then definitely it causes brittleness of the alloy, because if you're increasing more than 30%, your major or basic ingredients, basic constituents, that is your silver, tin, are reduced. Silver, tin are reduced means you are compromising on your strength and brittleness. Okay, here it is. Copper ties up with tin. Copper also increases the strength, but up to certain limits only. Now, it provides better clinical performance, less marginal breakdown. It causes delayed expansion with low copper alloys. Okay, because zinc will react with water, moisture. Okay, zinc can react with moisture, causing delayed expansion. Delayed expansion is again a property of your amalgam, which you have to remember. Okay, delayed expansion is also a property of amalgam. Common question can come from there. Reduces the amount of mercury necessary because it helps in reacting with the mercury. Okay, reduces emitted mercury vapor also. Reduces creep and marginal breakdown. Okay, it reduces creep and marginal breakdown. Increases strength. Must be used in admixed alloys. Okay, must be used in admixed alloys. So this is what is your indium does. Now, indium, there was one question yesterday, I guess someone asked to Dr. Ashfaq. Now, indium will affect, okay, that question was, one second. There was indium is added to amalgam. The explanation also says high copper amalgam alloys have significantly low creep values. This low creep decreases corrosion and solubility. But however, the increased copper content does not have any effect on brittleness, which is inherent with amalgams. Okay, now copper, as you increase more copper, brittleness also increases. That is one. But indium, the answer, the question and answer, they're not very ambiguous questions it is. But indium will decrease the gamma 2 phase. Remember that, not gamma phase, they'll reduce the gamma 2 phase. Okay, the indium reduces the gamma 2 phase. That's why it becomes more resistant to your, it decreases the creep, and it also becomes resistant to your corrosion and tarnish. Okay, it becomes more resistant to corrosion and tarnish. Now gamma phase, now you have gamma phase, that is your, okay, silver and tin, okay, silver and tin, which is unreacted alloy. Okay, that's the strongest phase, corrodes the least. Then you have gamma 1 phase, that is your silver and mercury, matrix for unreacted alloy, and second strongest phase after your gamma phase. Then you have gamma 2 phase, which is the weakest. Okay, then you have gamma 2 phase. This is like voids. Can you see these voids here? This is a gamma 2 phase. It corrodes faster, voids form, and corrosion yields mercury, okay, which reacts with more gamma. Okay, corrosion yields mercury, which will react with more gamma, leading to formation of gamma 1 phase. Okay, remember always gamma phase is the most strongest. Strongest if they're asking, it is gamma phase, and if they're asking the second strongest, it is gamma 1, and if they're asking the least, then definitely it is gamma 2 phase. Now this is what is the reaction which is happening here. Okay, silver and tin reacting with mercury, forming silver mercury and tin mercury. Okay, tin mercury is the weakest phase. Now in admixed alloys, you have something called as eta. Eta is your copper and tin. Copper and tin bind to form eta. Okay, that is what happens in admixed alloys, where you have little higher percentage of copper. And in single composition high copper alloys, you have more percentage of copper. Okay, there you form something called as epsilon. Okay, epsilon, that is Cu3SN. Cu3SN, okay, is the epsilon. Cu6 Cu6SN5 is eta phase, and this is epsilon. Okay, these two have more strength compared to your gamma 2 phase. Okay, remember eta and epsilon both have more strength than gamma 2 phase. Okay, phase transformation is seen with epsilon. Okay, phase transformation is seen with your epsilon phase. Okay, and here in your admixed alloys, eta and epsilon have more, okay, they are more strength compared to your gamma 2 phase. Weakest phase still is the gamma 2 phase. Okay, weakest phase is still the gamma 2 phase. Okay, if the question comes and the options are there, you have to remember that. Now methods of adding copper, then you have single composition lathe cut, where you have a lathe cut, then you have single composition spherical, where you only have spherical alloys. Then admixed, in admixed you have lathe cut and spherical, both. Okay. And then admixed, again you have lathe cut plus single composition. Okay, you have eutectic alloys and single composition also. Okay, that's what is admixed. This is the format. Now what happens in gamma 2 phase is gamma 2 phase dramatically affects creep rate. Okay, it will increase the creep rate. That's why we want less of gamma 2 phase. Okay, slow strain rates produces plastic deformation, allows gamma 1 grains to slide. That's what gamma 2 phase does is gamma 2 phase increases the creep because it forms more voids within your matrix. Okay, if you have more of gamma 2 phase, it is more voided matrix. Okay. Okay, eutectic and peritectic alloys. Okay, I'll tell you. Okay, now we'll first finish this. Now, gamma 2 phase is void. It's a void formation, okay, between the matrix, the core matrix of your silver tin and your silver mercury. So it causes silver mercury alloys to slide over it, which increases the creep. Okay, so we always want to reduce the creep, not to increase the creep. Okay, now high copper amalgams have creep resistance. Okay, they prevent the formation of gamma 2. Okay, high copper amalgam alloys will prevent the creep, and because they also have indium in them, high copper amalgam alloys, they'll prevent the creep. Now it requires greater than 12% of copper in total, okay, to be called as high copper alloys. Now single composition spherical, you have eta embedded in gamma 1 grains, okay, which interlock. In admixture, you have eta around silver and copper particles. It improves bonding to gamma 1. Okay. In admixture, it is improving bonding. In single composition, it causes interlock. Okay. Now the compressive, sorry, one second. Now the compressive strength, if you're seeing for compressive strength of the materials, okay, for amalgam, low copper, admixture, and single composition, for 1 hour and after 7 days. Okay, within 1 hour and after 7 days, if you see the compressive strength is least after 1 hour for admixed. It is the least after 1 hour for admixed. It is the least after 1 hour for admixed. And it increases after 7 days for admixed to 431. For single composition, because the spherical alloys, because they're all of single composition, maybe all are of spherical alloys, the compressive strength is high Okay, the compressive strength is high after 7 days and even after 1 hour. And in low copper amalgam alloys, you have less amount of compressive strength, okay, after 1 hour and after 7 days also. Now, if you're talking about creep percentage, low copper amalgam alloys have more creep because they have more of gamma 2 phase. In admixture and single composition, as you're increasing the percentage of copper, you are reducing the creep. Okay, and also indium you're adding, which you're reducing the creep percentage. Okay, in these alloys. In admixture, it is 0.4, and in your single composition, it is 0.13. Okay, remember. Now, but you're taking tensile strength. If you're talking about tensile strength, low copper alloys have more tensile strength compared to your admixed. Okay, low copper amalgam alloys have more tensile strength compared to your admixed alloys, and single composition, definitely all the properties are high except for creep percentage. Okay, this is what is for your compressive strength and tensile strength of your different amalgam alloys. We'll be discussing about the eutectic mixtures, peritectic mixtures. Individual chapters we'll be discussing once we finish this. Okay, this I'm just briefing you out this slide because these slides are those common questions: highest value, least value. Okay, these will be coming in your exam. Now, in casting defects, many questions have come on sprue. Okay, the first few questions are always on the sprue: why you want sprue, how it should be, at what angulation, at what position, what length. Okay, sprue has come many times, many twisted questions have come from sprue. Let's try to simplify what happens with the sprue. Now, there are three basic requirements why you want a sprue. Okay, you sprue the wax because you want to allow the most molten wax to escape from the mold. Okay, you want to allow the molten wax to escape from the sprue. Sprue must enable the molten metal to flow into the mold. See, once you have dewaxing, once there is dewaxing, okay, once there is dewaxing, you want the molten metal to flow, okay, into the sprue. Then the metal must remain molten slightly longer than the alloy that has to be filled in the mold. In this reservoir, you all know there's something called as the reservoir to which the sprue is attached. Reservoir is a place where it allows the molten metal. Okay, it keeps allowing the molten metal to flow into the mold cavity. Okay, it reserves. Okay, it keeps the metal complete. Okay, it doesn't cause metal fall short. Okay, now select the gauge sprue former with sufficient diameter. Now, one thing you should see is your sprue should have adequate diameter. If what happens if there's a large sprue former attached to a thin delicate pattern, it will cause a distortion of the casting. Now, how does distortion of the casting happen? When you have very small thin coping and over which you have kept a very broad sprue, okay, that will cause distortion. But if you're keeping a thin sprue diameter, okay, it's a small sprue, okay, if the diameter is less, it might cause suck back porosity. What do you mean by suck back porosity? It is the molten metal has not flown completely. The channel is narrow for a bigger casting. See, because you've used a narrow diameter sprue for a little larger casting. When you do that, the metal adequately doesn't flow into such a huge mold cavity. Okay, we want sprue as per the cavity mold. Okay, we want the screw as per the cavity mold. Okay. No, localized shrinkage porosity is on angulation of your sprue. Localized shrinkage porosity is on the angulation of the sprue. Okay, you have suck back porosity, which is inadequate flow of the sprue because of the gauge. Now, size, it should be at least 1.7 mm in diameter unless the pattern is extremely small. Okay, 2.5 mm diameter may be used for very large patterns such as bulky full crowns, or you can also use 2.5 to 3 mm of your diameters for your CPD casting, cast partial denture framework casting. The sprue is larger, thicker sprues. Okay, they are very in diameter, they are more. That can be used. Okay, so that is for your bulky crowns or castings. Now that has to be there for your sprue. Now, sprue former to be attached to the portion of pattern with largest cross-sectional area. Now, where should be the sprue attached? It should be attached to the portion of casting with largest cross-sectional area. Okay, and the length of the sprue should be adjusted such that the pattern is approximately 3 to 6 mm from the open end of the ring. Okay, you have casting ring, something called as casting ring. Okay, from the casting ring, it has to be 3 to 6 mm away from the casting. Okay, the pattern has to be 3 to 6 mm away from the open end of the casting, because once you're doing burnout procedure, all this wax has to go out. Okay, we want the wax elimination completely. Okay, if the wax elimination is not over completely, you will have gas inclusion porosities or pinhole porosities happening. Gas inclusion porosities is the left out remnant wax into the mold cavity. Okay, they form as gases. Okay, and they call small porosities or bubbles over your casting. Okay, so that's why you should have adequate this approximate length of the sprue such that you have complete dewaxing of the molded invested pattern. Now, in this two-stage burnout technique should be used whenever plastic screw formers are involved to ensure complete carbon elimination. Previously, they were also using plastic sprue formers. Okay, when you're using plastic sprue formers, you have to go for two-stage burnout because we want plastics have carbon, because we want all the carbon to be eliminated. Okay, even otherwise carbon might also cause your porosities. Okay, and metal sprue cannot be burned out, but must be carefully removed after investing the wax pattern. Okay, if you're using metal sprue. But we use only mostly wax sprues. No one uses a metal sprue or a plastic sprue. Commonly, okay, most commonly used is a wax sprue only. If they ask you what is the most commonly used sprue, is a solid wax sprue. Again, in sprues you have hollow and solid. What we use is a solid wax sprue. Okay. Now, sprue former is generally attached to the most bulky part of the pattern. Okay, the sprue former is mostly attached to the bulky part of pattern. Now, the sprue former connection to the wax pattern is generally flared. Now, whenever you're trying to attach the sprue former to the wax pattern, you flare it up. Okay, as you flare it up towards the reservoir, you also flare it up on the pattern. Okay, for high density gold alloys, but is often restricted to lower density alloys. Now, flaring will act as a reservoir. See, flaring will act as a reservoir, facilitating the entry of the fluid into the pattern. Okay, facilitating entry of the fluid into the pattern. Okay, that's why you need to flare the sprue former. Now, sprue position, some clinician prefers placement of sprue at the occlusal surface, whereas others choose the proximal wall, okay, that is your marginal ridge, or below the marginal ridge they use, okay, or just below a non-functional cusp, because we don't need to do major occlusal corrections. Otherwise, when you attach the sprue onto occlusal surface, you're trying to grind the occlusal anatomy also. And for such scenarios, most few people follow that the sprue is not attached onto the occlusal surface, but just below your non-functional cusp. Okay, to prevent grinding of occlusal anatomy and contact areas. Okay, and normally if they ask in the option, it is to be in the most bulky area only. Okay, it should be in the bulkiest portion of the pattern, sprue attachment. Okay, but it can also be attached to other areas also, where the thick cast pattern is little thick, not very thin. Now, ideal area for the sprue former is the point of greatest bulk in the pattern. Okay, see, the ideal area for sprue former is the point of greatest bulk in the pattern to avoid distorting thin areas of wax during attachment to wax pattern and to permit smooth flow of the alloy. Okay, sprue position, again, it is very important. Many a times asked question. Okay, they've asked many times question for sprue formers, so you have to remember that. Now, when the pattern is sprued at 45 degrees angle to the proximal area, a satisfactory casting is approved. Okay, always remember the pattern has to be attached at an angle of 45 degrees. Sorry, sprue has to be attached at an angle of 45 degrees to the pattern. Remember what is the angulation of sprue attaching? It is 45 degrees. Now, sprue length, if it is too short, wax pattern may be so far removed from the end of the casting ring that gases cannot be adequately vented to permit the molten alloy to fill the casting ring, resulting in porosity. That's why I told you, if you're wax doesn't completely eliminate, or the gases are not being come out, okay, completely from the investment, then it will cause resulting in porosity, maybe gas inclusion porosity. Okay, long and thin sprue formers. What happens with the long and thin sprue formers? Okay, it causes internal porosity called as shrinkage porosity. If you have long and thin sprues, the metal doesn't flow only, it is shrink before. That is what is your localized shrinkage porosities. Okay. Now, what should be your pattern placement? How should be your wax pattern? Okay, pattern must not be placed in the thermal center of the ring. It should be situated 3 to 5 mm from the top of the ring. Okay, it should be situated 3 to 5 mm from the open end. Okay, it has to be 3 to 5 mm from the top of the ring, and distance from the walls of the ring should be about 5 mm. Means if you have casting ring liner, okay, you all know about casting ring liners also. You have cellulose and asbestos. Okay, then your distance from the ring liner to the investment has to be around, sorry, to the pattern has to be around 5 mm. Now, most commonly used technique to provide investment expansion is to line the walls with a ring liner. Okay. Now, previously they were using asbestos as the choice, but is no longer used because it is carcinogenic. Okay. If they ask you a question, previously asbestos was used, but it is discontinued asbestos because of its carcinogenic potential. Asbestos as a ring liner is discontinued because of its carcinogenic potential. Now we use cellulose lacquers, but currently there are ring liners with ringless, without ring liner system. Okay, there are systems where you don't require ring liner. Okay, now placing the liner somewhat short. How short the liner has to be? It is 3.25 mm. Okay, the liner has to be 3.25 mm short of the ends. Of the end of the rings, the liner has to be 3.25 mm short. Okay, this also can be asked as a question in exam. How short? They can specifically give you the number 3.25 mm also. They can give 3 to 4 mm. If that is the option, choose that. If they specifically give 3.25 mm, then you have to choose 3.25 mm as the option. Okay, there is no other go. Now, wetting agent reduces the contact angle of the liquid surface. Now, why are you adding a debubblizer? Yesterday we were discussing about debubblizer. Okay, a debubblizer is added. Debubblizer is added to for the over the wax pattern such that the investment completely wets all the pattern. It completely flows over all the pattern. Okay. Now lower contact angle indicates that treated wax surface has affinity for water, which results in the investment being able to spread more easily over the wax. That's why we'll get a correct mold cavity. Okay, this is because we want to have a correct mold cavity. That's why you're adding debubblizer over the wax pattern. Okay. Now there is something called as zones of flame. They're asking. Sometimes they ask. There is unburned gas or cold mixing zone. Okay, unburned gas or cold mixing zone is the first zone. Then you have the conversion zone, where all the gases are reacting. Then you have reducing zone, then you have oxidizing zone. Now the zone which is required for melting of the alloys is the reducing zone. Reducing zone is the zone which is used for melting the alloys. Okay. Now if they ask you which zone is the last, then it is oxidizing zone. And if they're asking you which zone helps in melting, then yes, it is a reducing zone, which helps in melting the alloys. Okay, you have to use something called as reducing zone, that is the blue flame, which we have to use for your burning, okay, for melting of the alloys. Okay, now in short, how does the casting happens is, see, there's a wax pattern which you make, there's a wax pattern which you're making over the die, then you attach the sprue, okay, you attach the sprue at an angle of 45 degrees over the proximal surface, okay, and the pattern is placed at the center, okay, and it has to be from the, suppose this is the end, it has to be short, it has to be almost 3 to 6 mm, okay, from the end, such that once you do burnout, you'll have an empty cavity, okay, after burnout, see, this is the empty cavity, void, and then once you flow the metal, this is how the mold cavity is filled with. Remove the oxides, okay, over the investment. Pickling is done to remove the oxides over the investment. Okay. Why is rubber ring used in control water added technique? Control water added technique. What is that mentioned in your textbooks? Control water added technique? If so, can you just share a question or something from where did they take up? Because I have heard for the first time this. I'll try to see once now in the textbook. What is control water added technique? Rubber ring. No, rubber rings are with your without your casting ring liner. Okay, your rubber rings are they don't require casting ring liner. That's why they are used currently now. Okay. Control water added technique. I'll just see to it. Not recollecting it. Okay. So once you do pickling, then you remove the sprue, polish, and deliver it to the patient. This is how a proper casting is done. Okay. Commonly. One second. Chat. Someone has messaged. There was a question on the quiz. What kind of casting is used in controlled water added technique? Answer is rubber. What kind of casting ring is used in control water added? I'll find it out what is control water added technique. I've not heard of it, but I'll try to find it out. I'll just see if I have it with me. Okay. One second, we'll just go through cements now in a brief. There's a lot in dental cements also, which you have to know. Now, in dental cements also, there are few things like the setting time, mixing time, compositions. They ask you about compositions in dental cements or impression materials. That is common question. Okay. Now, this is what is the classification of dental cements. You have something called as water-based cements, resin-based cements, oil-based cements. Now, there is one question again, zinc polycarboxylate. Now, glass and resin modified glass ionomer cements are water-based cements. Zinc polycarboxylate is a water-based cement. Zinc phosphate is a water-based cement. Now, resin-based, you have composite and adhesive resins, and you have compomers, and then has oil-based. Now, according to Anasavi's, zinc phosphate is silver and copper salts, zinc oxide eugenol. This is based on the use. Okay, this is based on the use which you are talking about. Okay, which is used where? Yesterday in your mails, I forwarded to Ashfaq. Okay, so these are all depending on the usage. Okay, which is used where? Now see the film thickness, net setting time, compressive strength. Okay, now here the table gives everything almost. Okay, everything like the film thickness, the net setting time, and the compressive strength. Now glass ionomer and zinc phosphate luting consistencies have 2.5 to 8. Even polycarboxylate has 2.5 to 8. Okay, now for glass ionomer restorative it is 2.5 to 6. If you take about compressive strength, glass ionomer restorative has more compressive strength. Okay, as per the tabular columns from a textbook. Cement says luting agents. Okay, film thickness, this is not required. Okay, we have discussed about this only. Okay, solubility. We have discussed about solubilities also. Okay, solubility is maximum for zinc phosphate, and film thickness is also maximum for zinc phosphate. Now, if you're talking about setting time, it is more for your zinc oxygenol and zinc polycarboxylate. Okay, that's 9 minutes. It is more amount of setting time, that is at 100% humidity. The question is for 100% humidity, which they're asking. Now again, we have discussed about strength also. Okay, resin cements have more strength, compressive strength, and tensile strength also. Okay, they have both the strengths high, that is your compressive strength and tensile strength. Okay, so this you have to remember. If they are asking which is highest in compressive strength and tensile strength, then it is your resin cements. Okay, now we're talking about solubility. See, zinc phosphate has more solubility. Water-based cements are more soluble, okay, than oil-based cements. Water-based cements are more soluble than your oil-based cements, because water-based cements will mix in saliva and salt water, so definitely they'll have more solubility. Okay. That is not required. See, if you see cement thickness, the highest solubility is not for your. Here it is given maximum for this in the table as per textbook. But if you see, this also has 0.4 to 1.5. Yes, sorry, pardon me. The class ionomer has more, okay, as per the tabular column, but he has given maximum here. I don't know why. So if the option comes, better choose glass ionomer only. Okay, I would say better choose glass ionomer if the option comes. More solubility. Ultimately, water-based cements have more solubility than your oil-based cements. Okay, so glass ionomer, zinc phosphate, both are water-based cements.
Good.
Now we'll this. So these are the cements over time which have come. Okay, contemporary practice. Now we are using this only, compomers that is or resin modified glass ionomers or GIC. Cements. Okay, now fluorides many a times we'll be asking also which cement releases fluoride more or which cement releases fluoride less. Now fluoride ions released from restorative material become incorporated into the hydroxyapatite, that is your enamel, okay, or the dentine, which has so it becomes a fluorapatite. Fluoride acts as a catalyst for uptake of calcium and phosphate ions. So it causes acid resistant crystals and reduces the risk of caries development. Okay, so fluorides is used in dental cements. Okay, it is there present as an ingredient in dental cements also. Okay, fluoride accumulates in dental plaque, inhibits carbohydrate metabolism, and by acidogenic plaque microflora. Okay, so that's why fluorides are there. Now GIC and zinc polycarboxylate both have fluoride releasing cements. You have to remember that. Now silicate cement, we'll just briefly go with the silicate cement, first cement, that is the silicate cement which was identified. ADS specification number 9, silicate cement is relatively strong, okay. Now if you see the compressive strength of silicate cement is 180 megapascals. Tensile strength is 3.5 megapascals, and Noob's hardness number is 70. It is anti-corrosionic. Okay, even this cement is anti-corrosionic. Fluoride release, yes, we'll just tell you now what cement releases what fluoride. So even this is anti-corrosionic, means even this has fluoride release. See, even this has fluoride compounds. Composition. If you see composition clearly of your silicate cement, it has fluoride compounds such as sodium fluoride, calcium fluoride, and sodium aluminum fluoride. Okay. So this is also anti-corrosionic. Okay. Silicate cement is also now the first cement to be anti-corrosionic, then it would be silicate cement. If a question comes down like that, if the first cement, then silicate cement is also anti-corrosionic. Okay. Pulpal response, it causes severe pulpal response because pH is less than 3 at the time of insertion and remains below 7 even after 1 month. Okay, it remains below 7 even after 1 month. It is a severe irritant used as a reference to judge other materials. It is a severe irritant. Okay, it is used as a reference to judge other materials. Requires greater pulp protection. Now, pH of luting cements, again, I've told, we've shown you in the last PPT. What's the pH of the cements? Now, zinc phosphate, okay, zinc phosphate is commonly used previously, not now. Okay, high strength bases, orthodontic bands and brackets. It is two types, that is type 1 and type 2. Type 1 is fine grain for luting film thickness, and type 2 is for medium grain luting and filling film thickness should not be more than 40 microns. Okay, number 8, ADA specification number 8. Powder liquid systems, you all have mixed zinc phosphate in your second year and final year also. A composition, if you see the composition here, zinc oxide, magnesium oxide, okay, you have other oxides, silica, bismuth trioxide. See here, it doesn't have any fluoride in its composition. Zinc phosphate is not a fluoride releasing cement. Okay, the order of fluoride release, I'll tell you, but zinc phosphate is not a fluoride releasing cement. And if the question comes, which one is a not fluoride releasing cement, and if the option is there as zinc phosphate, yes, you can select that option. Okay. Now, zinc oxide is a principal constant. They can now they in questions, in few cement questions, they'll ask you what's the function of magnesium oxide in your zinc oxide cements, zinc phosphate cements. Then it reduces the temperature of calcination. Or if they ask you what's the function of aluminum phosphate, then you can ask you buffers and to reduce the rate of reaction. Okay, silica, it acts as a filler. So they'll ask you what is added for what. Manufacturing is not required. Mixing procedure. See, yes, you should know the ratio. It is 1.4 grams powder to 0.5 ml liquid. 1.4 grams powder to 0.5 ml liquid. Okay, remember the powder to liquid ratio for this cement. Okay, setting reaction, you have phosphoric acid attacks the surface of particles. Okay, how it goes, it's an exothermic reaction. Yes, it's an exothermic reaction. Very important you have to remember is it is an exothermic reaction. Okay. Now the working time is 4 to 5 minutes and setting time as per 96 ADA specification, it is 2.5 to 8 minutes. Okay, 2.5 to 8 minutes is the setting time. Okay. Control, how do you control the setting time and working time? You can reduce the powder liquid ratio. You can take more of a liquid which will fasten the reaction, or you can take more of powder that will also fasten the reaction. Okay, because of less liquid. Now mixing cements in increments and introducing small quantities of water. So what best you can do for controlling the setting time is mixing cement in introducing in smaller quantities and using of cool glass slab. You can use cool glass slab, that would be more ideal. Dimensional stability, okay, that's not required. Solubility, greater percentage of original particles bound to the matrix. Greater solubility is there in dilute organic acids. Okay. Tensile strength, compressive strength, we have seen. Okay. Compressive strength is up to 104 megapascals. Tensile strength is 5.5 megapascals. Modulus of elasticity is 13.5 gigapascals. Okay. It is a stiff and resistant to elastic deformation. Remember these compressive strength and tensile strength values. They might ask you in question, what is the compressive strength value? Just as a number, they can ask you in question in your entrance exams. So you should remember it is 104 megapascals. Okay. And pH, as we discussed pH also, okay, it will be in the range of 3 to 4 in the first hour. And after 24 hours, it reduces down to 5.5. Okay. So that's what is again in minutes, zinc phosphate, zinc silicophosphate, zinc polycarboxylate, GIC. We have seen, okay, it is 5.5, okay, after 24 hours, still less. Now zinc polycarboxylate, okay, if they ask you, it is the first cement, okay, it is the first cement that developed an adhesive bond to tooth structure. It is one important question you have to know, which was the first cements which adhere to the tooth. Both zinc polycarboxylate and GIC are both adhering to the tooth. If the option is there, both A and B, or like both zinc polycarboxylate and GIC, then the option would be zinc polycarboxylate and GIC both adhere to the tooth chemically. Both adhere to the tooth chemically. Okay, both adhere to the tooth chemically. Now see, if you see here in the composition, polycarboxylate is a fluoride releasing cement because it has, see, it has stannous fluoride. It has stannous fluoride in its composition. It has stannous fluoride in its composition, and it imparts anti-carcinogenic properties. Now, stannous fluoride imparts anti-carcinogenic properties to your zinc polycarboxylate. Okay. Then you have polyacrylic acid, that is the basic ingredient. You have itaconic acid and tartaric acid. Okay, these are all present in your zinc polycarboxylate cement. Now, setting reaction not required for you. Setting time 6 to 9 minutes, working time 2.5 to 3 minutes. Now, how would you affect setting time, working time? Higher powder liquid ratio, that is more powder and liquid, you will decrease the working time. Increased temperature will decrease the working time. Cooling the glass slab will increase the working time. Okay, so many a times a question comes on working time, setting times. So you have to remember how it is decreased, how it is increased, what would be the ideal method. Now, yes, if they are asking you, this is the twist of a question they ask you commonly, what would be the ideal method of altering the working time or setting time means it should be cooling of the glass slab, because if you're trying to do with other methods like increasing the powder liquid ratio or increasing temperature, you're trying to compromise on the strength properties of the cement. So ideally, when you're trying to increase, the ideal would be cooling of the glass slab. Okay, it would be the cooling of the glass slab you have to remember. Okay, water settable cements. Dew point. Dew point is at the point where like moisture, the cement has moisture content in it. Oh, wait a second. I'll show you a slide, then you'll understand. Dew point is dew point is the atmospheric temperature, okay, below which the water droplets begin to condense and dew can form. Okay, when you have more dew point means you have more moisture, okay, in the air. Okay, when you have more dew point, you have more moisture in the air. So it has to be always less. What's the other question you asked? Pardon me. If addition of retarder is there in the options, so then which to choose? See, if you're adding retarder also, you're trying to, what do we say, compromise on properties. Okay, so it is always better, ideal, if they're asking, it is always better to choose on cooling of the glass slab. Okay, what would be the effect of cooling glass slab below the dew point? Now, when you have a dew point more than 20 degrees, okay, that is considered to be uncomfortable. Okay, that is called as a frost point in cements. More than 22 degrees is more than 20 degrees, sorry, is like frost point for cements in dental cements in dew points. Okay, it should be always 20 more less than 20 degrees when you're trying to cool the glass slab. Okay, if it is more than 22 degrees, it causes more moisture accumulation. Okay, you'll have more water. Okay, that's what is dew point consideration in dental cements. Wait a second, I'll need to share a slide. I guess it's there ahead. We'll see. 1 second. Okay, I'll search for dew point. One second. Once again, okay. You can see thermal properties of dental materials. Here they have given for dew point the atmospheric temperature varying according to the pressure, okay, and humidity, below which droplets begin to condense and dew can form. Not a clear explanation I'm not finding anywhere to these dental materials or at the seminars. Okay, dew point greater than 20 degrees is considered uncomfortable and greater than 22 degrees is considered to be extremely humid. Okay, so what happens basically is if you have dew or moisture, even that can affect your properties of dental cements. Okay, if you are having water-based cements, okay, you have two types, water-based and oil-based. And definitely for water-based cements, again, it can affect your properties. Okay, but still, if they're asking you ideal option, then you have to go with the choice of cooling of the glass slab only. Okay, but it should be not below the dew point. Okay, it should not be below the dew point. Okay, that's what you have to remember in answering these questions. A proper answer, I'm not finding it. I'll try to search for it, what exactly it is. Okay, proper answer is not yet with me, but this is what I found out. This is what is dew point. Okay, the higher dew point indicates more moisture in the air. That's what is there. 1 second. Just need to connect my charger. Sorry, audio is on now. Are you able to hear me?
Yes, sir.
Okay, okay, fine. Sorry, I didn't see that. We'll just go back to the slides. Now, zinc oxide divisional cement, you have four types. You have type 1, type 2, type 3, and type 4. Type 3 is also called as your intermediate restorative material, IRM. Okay, remember that, which is used for cementing your temporary crowns after your tooth preparations. Okay, type 1 as a temporary restorative material, type 2 as a permanent cementation material, and type 4 as a cavity liner. Okay. Now this is what is a basic composition. Now what does the zinc acetate do? What is what? You have to know these compositions. Okay. Mixing procedure, you all know. We're not going into mixing procedures in depth. Now here they have given a table where they've shown temporary, permanent filling materials. Okay. Different setting time and all, which is not so frequently asked. So not required. We'll just rush through it. We have other cements more. Z2 is not such an important one. Okay, see here in your compressive strengths for EBA and polymer modified ZOEs. For EBA, the compressive strength is high, that is like 64 to 65. And for polymer modified ZOE, it is 37 to 48. Elastic modulus, it is tensile strength is 6.9 to 7 for EBA. And for polymer modified, it is 3.8 to 4. And for your bond elastic modulus is 5.4 to 2 and 2.7. Bond strength to dentin is 0 for both. They don't bond to dentin because they're not chemically bonding cements. Okay. Here is your solubility ratio. If you see, it is 0.02 to 0.04, 0.08. Because they are oil-based cements, they have less solubility. Because they are oil-based cements, they have less solubility. Okay. Resin cements, you have three classifications: class 1, 2, and 3. Class 1 is self-cured materials, class 2 is light cured materials, class 3 is dual cured materials. Okay. Class 1, 2, and 3 have film thickness maximum of 50 microns, and class 1 and 3 have working time minimum of 60 seconds. Class 1 and 3 and setting time of maximum 10 minutes. Okay. Class 2, because they have light cured, their depth of cure depends. Okay. You have to cure it by light. The setting time is how much ever you can. It is up to us because they are light cured. Okay. Now class 1, 2, 3, the water absorption, that is water absorption, is maximum, that is 40 micrograms per millimeter cube. Solubility also, if you take, they have fine amount of solubility, is like 7.5 micrograms per millimeter cube. Okay, now use of resin cements, they have cementation of ceramic or resin inlays and onlays. Okay, they're used for cementation of ceramic veneers, cementation of orthodontic bands, direct bonding of orthodontic brackets, and cementation of all metal castings. Now, composition and chemistry, when we are discussing resin matrix, this is not required. Compositions you have to read. We'll see about, okay, no. This we've discussed. Okay, this we have also seen the tensile strengths. Okay, for resin cements, they are high. They have high tensile strength and compressive strength compared to other cements. Okay. Now, film thickness. If you see for these resin cements for different brands, that is Panavia, Calipra, and all, this is not required as such. Okay, wait. We'll just go through another one. We'll just go through physical properties. Okay. We'll just go through this physical properties once. Now in physical properties, your viscosity, okay. Serpent. Both are metal modified GICs. Okay, your serpent and serpent both are metal modified GICs. Sintering process, maybe I have to, when I don't remember much on cements, I've not been reading cements. I'll just get through these questions once again. Okay, I've noted down. Again, in the second session in the evening, I'll just come back with all these answers. Dew point, cement, okay. These are two complicated questions or ambiguous questions which have been coming. So we'll discuss with that. But both are metal modified GICs as such. I don't think so there's a difference, but I'll find it out. Okay, one second. Now in your physical properties of materials, then you have something called as viscosity, which is resistance of a liquid to flow. Okay, all the materials possess some form of viscosity. Okay, rheology is the study of deformation and flow characteristics of matter. Now, if you take zinc polycarboxylate cement and resin cements, they have more flow, okay, than compared to zinc phosphate cement, okay, because they have less viscosity. Now, stress is strain. We're not going much on stress strain. You all know the definition. Yeah, but you should know based on rheology, there are four behavior fluids are classified into four types. That is Newtonian, pseudoplastic, dilatant, and plastic. Okay, Newtonian, pseudoplastic, dilatant, and plastic. There are questions come many time on these. That is Newtonian, pseudoplastic, dilatant, and plastics. Okay, if you see Newtonian, we have fluid as the ideal fluid. Okay, the stress and strain are directly proportional. It has a straight line axis. The liquid has a constant flow. Okay, it exhibits a constant viscosity. The slope is constant. Okay, in your Newtonian liquids, the slope is constant. They're called as ideal behavior. Okay, ideal fluids. Then pseudoplastic, okay, viscosity decreases with increase in strain. You increase the strain, the viscosity decreases. With increase in strain, shear stress rate increases to reach constant value. So after some time, it goes as a flat curve. Okay, these materials exhibit a pseudoplastic nature where after certain amount of strain, the stress remains constant. Okay. Now dilatant, this is opposite to pseudoplastic behavior, means as you keep on increasing the shear strain rate increases, the viscosity increases. As you keep on increasing the shear strain rate, the viscosity increases. Now plastics, okay, they don't flow, but they need some amount of force to flow. Okay, that's a ketchup in a bottle. It's a classic example. They exhibit a rigid behavior initially, but attain a constant viscosity after some application of stress. Okay, try to push, apply some force. After that, only they try to have a certain amount of viscosity. Okay, thixotrophic material, that is viscosity of most liquid, decreases rapidly with increase in temperature. That is not required. Thixotrophic, that is a polishing paste. No. Yes, creep has been asked. Time-dependent plastic strain of a material under static load or constant stress. Under static load or constant stress, you have to remember. Okay, creep of amalgam, sag of metal ceramics. Amalgam have creep. The creep is reduced in your high copper amalgam alloys, as we have discussed. Okay. Amalgam creep, that is because you'll have delayed expansion in amalgam because of creep. See the delayed expansion of your amalgams. Okay, amalgam placed with allowing minimal dynamic creep values. Flow is generally used in dentistry to describe rheology of amorphous materials such as waxes. Color, we are not going. U value chroma, yes, color, when we're talking color, you should all know about U value chroma. Now, U is the dominant color of an object. U is the dominant color of an object. Okay, it describes a particular color of an object, that is red, green, or blue. Okay, refers to dominant wavelengths present in spectral distribution. Okay, so it's a particular color of an object if you're talking about U. Value is relative lightness or darkness, how bright or how dark the material is. That is relative lightness or darkness of a object is value. Okay. Now for each shade can be separated into lighter and darker values from 0 to 10. 0 being black, 10 being white. Okay, now yellow of a lemon is lighter than red of a cherry. Okay, that's how you value the objects. Chroma is degree of saturation. For a specific color, you can have like pink, again you have different pink. Yellow, again you have dark yellow, lemon yellow, light yellow, something like that. So that is what is saturation, how saturated the solution is. Okay, that's what is your chroma or intensity. Saturation or intensity of a color is what is your chroma. Now U changes in a circumferential direction, and if you see previous slide, now U changes in a circumference. Value vertically. Value changes vertically. Okay, and chroma radially. So these three are there in long axis. Three different axes. Color of gingiva and Munsell scale. Color of gingiva and Munsell scale. Is it given? One second. Oh. Now, color of gingiva is mostly used in C-lab system only. Okay, here whatever the studies are given as C-lab system, they've not mentioned in Munsell. Wait a second. Wait a second. Not mentioned here. Okay, here this is how Munsell describes. Okay, so in red hue, okay, you can see in the chroma intensities how to choose a gum. Basically, they have not mentioned in C-lab systems. They have mentioned different gingival tones, but they have not mentioned in Munson scale. It was where, can you just write down the question also? Where is it? What are the options? Have they given a reference to that? Let us see that also. Okay. But in general, this is how your U value and chroma are. U is circumference, value is vertical, chroma is radial. Okay. Five yards, 6 by 4. Now reference, what have they mentioned the reference anywhere? Have they given in the explanation the reference book or what? No reference. Okay. I'll find it out. Munsell scale, because I have read in C lab only. Munsell scale I have to see, because as such there is nothing related to gingiva and Munsell. You have shade tabs available for gingiva. Yes, you have shade tabs available in gingiva, but Munsell I have to find out, because textbook doesn't mention on Munsell. Textbook has only mentioned on the tooth color. Still, I will find it out, these questions, because these are few questions. If they come down, we have to answer it correctly. Even this new to me, I should also know. Okay, we'll share back. Okay, a shade guide. Shade guide is used to perform color matching. Okay, in different operatory. Okay, so shade tab, it's there. Metamerism, you should also know about metamerism, that objects which appear color matched in one type of light, they appear different in under other light source. Okay, that's what is metamerism. Okay, so in different light sources, they appear different. See here, it appears bright blue. And always remember what could be, if they ask the question, shade selection has to be done in what? It's definitely natural daylight. Shade selection has to be done in natural daylight. Fluorescence, energy that the tooth absorbs is converted into a light with a longer wavelength in which the tooth actually becomes the light. So that is what is fluorescence. Fluorescence means emit. The tooth or any object which absorbs that energy will emit back. That is what is your fluorescence. Okay. Now then, other things what you have got is your thermal conductivity diffusivity. They don't ask you much on this. Okay. But they'll ask you on tarnish and corrosion. You should know what is tarnish. Tarnish is just the discoloration. Okay. Corrosion is actual loss of the material. Tarnish is just the discoloration of the process. Metal surface is dulled or discolored. Okay, oxide formation, but it is not the loss of the material. Okay, it's just the alteration of surface finish or luster. Once the tarnish start, yes, definitely will proceed into corrosion later. Okay, so corrosion is definitely loss of the metal because of oxides. Okay, over time. So tarnish will happen first, then happens the corrosion. Okay. Now classification, again you have chemical or dry cell corrosion. Then you have electrochemical or wet corrosion. Again in wet corrosion you have galvanic corrosion, stress concentration, stress corrosion, and concentration cell corrosion. Okay, we're not going to electric more. These three you have to know. Because galvanic shock, what happens is when you have two different metals in opposition. Okay, this forms as a circuit. Anode and cathode, the saliva acts as the electrolyte. Okay, which will form as a circuit, causing a electrolytic cell consisting. Okay, electrolytic cell corrosion. Okay, this happens when you have two different. When you have a gold restoration in the upper, amalgam restoration in the lower, they form electrolytic cell that will lead to electrochemical cell corrosion. Okay. Now stress corrosion is there, concentration cell corrosion, crevice corrosion. Okay. Protection against corrosion, passivation. Yes, passivation is passivation of iron with chromium and passivation of tin due to tin oxide formation. These are done for passivation. Passivation is a forming of a thin layer of oxide over the metal, okay, which tries to protect these underlying layer from corrosion. Okay, that is what is your passivation. Wait a second. Wait a second, we're going through mechanical properties. Here you have one more important thing in your mechanical properties. Okay. Now strain, what is stress? What is strain? You all should know modulus of elasticity is what? Stress by strain. Okay, now stress by strain is the modulus of elasticity. It represents the stiffness of a material within the elastic range. Means if you're trying to pull the material, okay, till the modulus of elasticity, it will come back to its original form. Okay, beyond it, it will rupture. Okay, it defines the represents the stiffness. Okay, now strength, again you have ultimate tensile strength, shear strength, compressive strength, fractional strength. Proportionality limit, it's the greatest stress that a material will sustain without deviation from proportionality of stress to strain. Means it is a constant after which the material will break. Now resiliency, it is the amount of energy absorbed by a structure when it is stressed to its proportional limit. Okay, or it is the resistance of material to permanent deformation. Now, what is the difference when you're asking about elastic modulus or one second, diametral tensile strength? It has to be here. Okay. Resiliency and or modulus of elasticity, if you check. The modulus of elasticity represents the stiffness. It is not a sort of energy absorbed by the material. Now, resiliency is the amount of energy absorbed, okay, by a structure when it's stressed to its proportional limit. Now, what is proportional limit? It is the greatest stress that a material will sustain without deviation from proportionality of stress to strain. Okay, even your modulus of elasticity is stress by strain within elastic limit only. So actually all three are almost similar, but with a slight difference. Now where the difference lies here is, your modulus of elasticity is the stiffness, okay, how hard or how rigid the material is, okay, until stress by strain, okay, it is by stress by strain up to a limit. That limit is proportionality limit. Okay, it is the greatest stress that a material will sustain without a deviation from the proportionality of stress to strain. Diametrical yield strength. Wait a second. These are direct definitions which you have to remember. One second. 1 second. Okay. Now, if you see here, the definitions from the textbook, if you're seeing, okay. Diametral tensile strength. Spring back in terms of yield strength and elasticity. 1 second. Okay. Now, elastic modulus or Young modulus, okay, it describes the relative stiffness or rigidity of material, which is measured by slope on the graph actually, which will explain this correctly. See, now here, if you see this graph, okay, here if you see this graph, UTS is the ultimate tensile strength, YS is the yield strength, P is the proportionality limit. Now here the E is the elastic modulus, okay, or modulus of elasticity. Okay, for a certain material, dilatant and pseudoplastic. See, dilatant is a liquid, okay, wherein after certain, okay, you apply stress, after certain amount of strain, it flows more. The stress keeps on increasing proportionality, as I told you. Okay. Now for dilatant, what happens is, for dilatant, your viscosity keeps on, for a dilatant, the viscosity keeps on increasing. Okay, the viscosity keeps on increasing after certain amount of strain and stress. Okay, but in pseudoplastic behavior, it is opposite of dilatant, wherein the after certain amount of strain, okay, the stress remains same, but after certain amount of strain, the viscosity also doesn't increase. There is a flat curve. Wait a second, we'll share that slide again, graph. If you can see this graph clearly, so the plastic is a, okay, plastics are what? You have to apply certain amount of stress, after which only they start flowing under constant viscosity. Okay, you have to apply a certain amount of stress, after which only they start flowing into constant viscosity. Dilatants, after certain amount of strain, the viscosity keeps on increasing. Okay, after a certain amount of strain, under stress, the viscosity keeps on increasing. Now, Newtonian are ideal. As and when the strain and stress are increased, the viscosity also keeps on a constant graph, a constant growth. But in pseudoplastic, it is opposite of dilatant, wherein after certain amount of strain, okay, after certain amount of stress, the strain keeps on increasing, but still the viscosity doesn't change. It is static, it is flat, it's a flat curve. Okay, after certain amount of strain application, it remains constant. Okay, Newtonian constantly keeps increasing as and when the forces are increased. Okay, and dilatant after certain application of strain, okay, it keeps on increasing on stress. Plastic, you need certain amount of stress to induce viscosity into those materials. Now, if you take about this graph, okay, stress and strain plot for a stainless steel orthodontic wire, okay, the proportionality limit, okay, if you see, now in the definitions, elastic modulus describes the relative stiffness or rigidity of the material, okay, which is measured by the slope of the elastic region on the stress strain graph. Now here, this from here to here, from this E, have you seen this E measurement? Okay, so what it is, if you take P, 1020 divided by how much at 0.5053 strain percent, okay, which means what is elastic modulus stress by strain? What is elastic modulus stress by strain? Which the material will come back to its original shape or form. It will not distort. Okay, after which until the yield strength, it will go on. After ultimate tensile strength, it fractures. Ultimate tensile strength is the strength after which the material ruptures or fractures. Okay. Limit, it deforms. The material deforms. Okay, and after yield strength, up to the ultimate tensile strength, then the material fractures. If you see this graph, P is the proportional to limit, before which the material can come back to its original shape or form. Okay, you can bend how and you like and get into original without altering the properties of the material. So what is happening here is, if you take E, proportionality limit is 1020. 1020 is the stress divided by the strain. Okay, you are getting the elastic modulus. Okay, that is what is your proportionality limit or elastic modulus. Next, wait a second there. Now, if you take resiliency, okay, resiliency is what the amount of energy absorbed. Okay, this is what resiliency. If you see here within the elastic strain, see this diagram here. Okay, if you see this graph, here is the proportionality limit. Okay, this is the toughness. This is the resiliency. It is within the elastic strain. Okay, it is within the elastic modulus. It is the amount of energy absorbed by the material. Okay, it is the amount of energy absorbed by the material. Okay, and then there comes toughness. The rest is plastic strain. Now, ultimate tensile strength also, here there are two, UTSA, okay, A and UTSI. What are those UTSA and UTSI? Now, in this case, the proportionality limit remains constant. Perhaps how much time back I read this. Okay, wait, I'll try to simplify these in the afternoon session. It will be more complicated for me to read everything now for you all. I'll try to simplify. It's been a long time I've referred this. I'll try to simplify these in the afternoon session to you all. Okay, but this will be from Philips only, such that any ambiguity will not be there. Okay, we'll try to simplify for you this in the afternoon session. Okay, there's another afternoon session today, if you all remember. from 2 to 4. Okay, don't forget. Okay. And yes, dispersion and transformation toughening also. These few things I have to refer back Phillips once again to get your proper answer. There's everything there here. We'll try to simplify it. Okay. So today, okay, we finished 2 hours. 1 second, I'll just. One second. One second. Wait a second. Now here they've. What was the question on estrogenicity? Have they asked in paper? Can you just elaborate the question? Because estrogenicity was because of bisphenol A and bisphenol A dimethacrylates. Bis GMA, yes, they do affect. They do have estrogenicity. Okay, that's what has been mentioned. They have seen tested samples. There was estrogenicity to bisphenol A and bisphenol A dimethacrylate. So bis GMAs do have estrogenic activity. That is what is been given as per the studies. Okay, and metallurgy I'll cover in the next session. There is a lot in metallurgy, from the alloys to their compositions to their casting defects. There's a lot in metallurgy to cover. There's a lot actually in DM. 2 days, just 4-5 hours. It's a big task. Okay, I'm just running away. I don't know. I've missed many points also. Okay, this is what is for bis GMA. Yes, it has estrogenicity activity. But I want to know the question what it is. Is it there with me? Just we'll go through the questions first. Few. 1 second, we'll just see a few questions. Now in the stress strain graph, the area bounded by elastic region is now we'll see these papers once again. Now, there's first question here in stress strain graph, the area bounded by elastic region. Okay, that's the elastic limit, which is measured radially. outward from the neutral axis. Radially outwards is chroma. Okay, radially outwards is your chroma. Oh, sorry, it's toughness. 1 second. No, it is not toughness. It is resiliency. It is resiliency. I've shown you the graph. See, if you've seen the picture, even now I can recollect. Wait, I'll share again the same graph. If you see here, see in the elastic limit, it is resiliency. Classic diagrammatic question. Okay, classic diagrammatic question they've asked directly from this graph. Within the elastic limit, this is what is the elastic limit from the proportion limit. This is the elastic strain. Okay, this graph. And that's what is resiliency. Toughness is beyond. Okay, toughness is beyond within plastic range, plastic strain also. Okay, so that's what I'll try to simplify these with other graphs. This graph is looks little confusing, but here they've classically mentioned resiliency here. Okay, so resiliency is the answer for that. Okay, we'll see other questions also. If you see few questions, we'll come to know what it is. Liquids that show higher viscosity as shear rate increases are known as. Liquids that show higher viscosity as shear rate increases are called as pseudoplastic. Are called as pseudoplastic. No. Dilatant. Sorry, dilatant. Pseudoplastic will not have. That's what dilatant will increase as you have shear stress. The strains remain constant. Okay, I have to also talk about hardness stress. We'll discuss those also. That is also important. Van der Waals forces are example of they're not ionic bonds. They're not covalent bonds. They're just as secondary bonds. Yes, they are secondary bond. Few questions they've asked. Grayscale is value. Okay. The phenomenon of transformation of solid directly to gas is sublimation. Okay. Ductility can be measured by percent elongation decreased in tensile specimen, cold bend. Yes, all the above it can be. Teeth that appear to be color matched in one and may not appear in another color. Yes, metamerism. Direct definition questions, definitions we have to remember. Okay. Percentage elongation. Okay, we'll see percentage elongation also we have to see. Once in system, the value increases towards top and decreases towards bottom. Yes. 12 is A. The heat required to evaporate the vapor ongoing of water is heat of latent heat of vaporization. Yes. Which of the following is a primary bond, ionic, covalent, metallic? Yes, it is all the above. Surface energy is maximum for enamel. Okay, surface energy is maximum. See, if you can see the order of surface energy also, enamel greater than dentine, greater than gold alloy, greater than pure titanium, greater than Teflon. Okay, greater than enamel, greater than dentine, greater than gold alloy greater than pure titanium gold than greater than Teflon. Impression materials, mostly we've covered it. Out of gold and titanium, which is more biocompatible? Oh, if you take biocompatibility, titanium. Titanium, because gold cannot be used for osseointegration. It doesn't allow cells to grow on the surface of gold. But titanium, yes, it allows its surface for the cells to grow on and help in osseointegration. Gold doesn't osseointegrate. There is no research of gold as an osseointegrated material or never has been tested as a long-term study. Okay, so yeah, but as a restorative material, if you were to ask the question, gold as a restorative material is obviously better because yes, gold fillings and all. Titanium doesn't have the ductility and malleability. Gold has the best ductility and malleability among all the metals which are available. Okay, so as a restorative material, if you are seeing, yes, gold is best. Okay, and but if you're talking about biocompatibility, yes, titanium is always better. Okay, titanium is the most biocompatible material we have till date. Okay, for the body. And if it's about restoration, you can opt for gold. Now, shelf life of polyether. How is the shelf life of polyether? The question number is, and I don't remember, it is 45. 45 is A. Now shelf life for polyether is 2 years. Okay, even I didn't know this. This question has come. Okay, liquefaction is 70 to 100 degrees. Gelation, okay, 37 to 50 degrees. Least shelf life for due to oxidation of tin component. Now, okay, the advanced least shelf life would be for condensation silicone only. Tin component is there in condensation silicone. So I'll just see the answer. Okay, that's B. That's B only. Okay. Yes, condensation silicone. Now, percentage of brush heap structure in agar. Okay, 13 to 17% brush heap structure. Less tall. In agar, if you are asking, you major content is of water only. Okay, agar is 13 to 17% only, giving brush heap structure. Water is the major content in agar. Okay, in the composition you have to know agar compositions. Okay, we have discussed that. Metallurgy, okay. Fins and all, yes, casting defects we to discuss. See, ring liner short of casting ring pipe. Okay, the option is here. Oh, see, they've given 3.25 mm has to be the answer, which we have discussed. Okay, if they give you ring liner short of casting ring. So this is what is your casting ring and it the ring liner. Okay, it has to be big 3.25 mm. Okay, now what is alloy and all we'll discuss in the evening session. Maximum carbon content of steel used in dentistry. Maximum carbon content of steel used in dentistry is around 3% to 1.7%. What was the question number? 11. 11 answer is 1.7%. Yeah, 1.7%. Yes. Bonding of porcelain to metal restoration is chemical and mechanical. Yes, it is both. Okay, both of the above it is. The best biocompatible dental casting alloy. Okay, the question has come here. Casting alloy. Okay, what was the question? Number 9. Yes, titanium. See, the answer is titanium. Okay. Most biocompatible material is titanium only. Okay, if you take biocompatibility, it is titanium. Okay. They asked a question also. Best biocompatible dental casting alloy, then yes, it is titanium. Okay. The principal cause of localized shrinkage porosity. Too rapid solidification, which allows all the wires to segregate. Okay. See all the options always. Premature termination of flow of molten mineral during solidification. That is what is localized shrinkage porosity. Okay, in the afternoon session, we'll try to solve few questions. Here they have given crystal structures also. crystal structures. If you want to remember the crystal structures, depth chamber gas is another name of cyanide vapor. Yes, cyanide vapor is called as depth chamber gas. Okay, is another name of cyanide vapor. Okay, we'll go through such questions. I'll also go through such questions which will give us an idea. Sprue angle is 45 or 135 degrees. Okay, so we will see you in the afternoon session. Okay, till then we'll end the meet. Okay, you just keep the questions ready for afternoon session. I'll try to find out what is dew point, what is pyroplastic. There's dew point, and we have to also know about cement and cement. Okay. Yes, Munsell scale. I'll find out. Diametric tensile strength is given in the textbook. I'll try to simplify what exactly it is for you. And spring back terms in yield strength and elasticity. That mechanical properties will go ahead more detailed in mechanical properties and metallurgy. This okay. This will solve. One more second. This PPT, I'll share it away. This will give you just idea on few questions. Okay, so that you can refer it back. The setting times and all these for the materials, restorative materials. Okay, I'll send it to Ashfaq. He'll forward it to you. Controlled water adder technique also, I'll try to find out. I have not heard about it anytime, but I'll try to find it out what it is. Controlled water adder technique. That's a new question to me also. Thank you for asking a few questions. It's very interactive. Okay, to know few things. Okay, when you are out of touch with the syllabus. Okay, I'll try to find out that also. What is controlled water? See, ringless system is most commonly used system now currently. Or ringless casting system is being the most commonly used system now. So onto which how it is into control water adder technique, I want to know. Even I'll find out that. Okay.